Hello, everyone, and welcome to the AIST Environmental Sustainability and Energy Conservation webinar. This webinar, organized by the AIST Middle East and North Africa chapter, and is also sponsored by Heister. Before we begin today's webinar, I would like to touch on a few housekeeping items. First of all, this webinar is under the guidance of the AIST Antitrust Compliance Guidelines. So please, during this webinar, do not discuss with others your own or competitors' prices, pricing procedures, or anything that might affect prices such as costs, discounts, terms of sale, profit margins, or anticipated wage rates. And please do not make statements about your own prices or those of competitors. And do not talk about what individual companies plan to do in a particular markets or with particular customers. A few reminders that all attendees are muted during this event. Questions to the presenters may be submitted via the Q&A feature, which you can find at the bottom of your Zoom tray. Submit your questions through that Q&A feature during the presentation, and at the end of the presentation conclusion, the moderator will relay the questions to the speakers. This is a live session, and we are recording this session for later distribution, but we ask that any of the attendees refrain from taking any photographs or recording of any of the presentations. Those actions are strictly prohibited. At this time, I would like to thank our webinar sponsor, Heister Company. Today's webinar brought to you by the Heister Company. Heister is a global manufacturer of forklifts, high-capacity lift trucks, and container handling equipment for the metals and steel industry. With strength, durability, and a range of electric power options, Heister can help you meet sustainability goals without sacrificing performance. Please visit heister.com to learn more. That's HYSTER.com. At this point, I would like to introduce our moderator, Mr. Karim Alshurafa. Mr. Alshurafa is a general manager of sales and marketing for the SMS Group in Pittsburgh, Pennsylvania, here in the United States. Mr. Alshurafa has held multiple leadership positions within AIST. He is currently the vice chair of the AIST Middle East North Africa chapter and the AIST Pittsburgh member chapter. He has also served as past chair and officer with the AIST Oxygen Steelmaking Technology Committee. Mr. Alshurafa has a Bachelor of Material Science and Engineering and a Master's degree in Engineering, Entrepreneurship, and Innovation from McMaster University in Hamilton, Ontario, Canada. He has 16 years experience in primary steelmaking and secondary steelmaking technology, beginning in 2004, where he was an EAF process engineer at Gerdau Ameristeel Whitby in Canada. He's also been a sales engineer at Heraeus Electronite and Steelmaking Sensors. And in 2013, he joined the SMS Group as a senior engineer in the Steelmaking Metallurgy Department prior to his current position as the general manager of sales and marketing. And finally, Mr. Alshurafa is a veteran of the Canadian military. Mr. Alshurafa, we thank you for your service. At this point, I would like to hand the program to Karim Alshurafa.
Thank you, Brian, for the introduction, and thank you all for joining us today. The AIST MENA chapter welcomes you all. We're very excited about our webinar today. We have 4 presentations that will be held in the following sequence. Dr. Karim Badr from RHI Magnesita is the marketing director for the Middle East. He will be presenting on the review of hydrogen steelmaking routes. Dr. Thomas Buergler is the head of R&D in Ironmaking and CEO of Metallurgical Competence Center at voestalpine Steel Division. Will be presenting on the CO2 neutral steelmaking efforts over the past decade. Mr. Alberto Briganti is the Chief Sales Officer, the Italy and MENA region for the SMS Group. He'll be presenting on the combined efficiency of green HBI, DRI with smelting technology in the MENA region. We'll also have Dr. Amr Abdelghani as the Assistant Professor and Faculty of Engineering at Cairo University present on the steps to produce greener iron in the MENA region. Without further ado, here we're going to get started in the program. I would like to introduce Dr. Karim Badr in more detail. Dr. Badr holds a bachelor's degree in mechanical engineering from Alexandria University in Egypt and a master's degree in engineering management from Arab Academy for Marine Transport and Engineering, Management Material Science from Sheffield Hallam University in the UK. In 2007, he earned his PhD in reduction metallurgy from University of Leuven in Austria. He has been employed by RHI Magnesita and its predecessor company, RHI AG, since 2013, where he serves as North Africa sales manager for the steel division. In August 2020, he was named marketing director, steel division of RHI Magnesita. But Dr. Badr began his professional career as a DRI operations engineer for AIST in Egypt, and before then becoming a research assistant at the University of Leuven. After leaving academia, he was named product manager, global marketing development for RHI AG, and marketing and sales manager for Kuttner GmbH in Germany. He has had a number of published papers on iron ore reduction, refractory solutions, and electric arc furnace operations. Please welcome Dr. Badr for his presentation. Dr. Badr, please unmute yourself. You can get started.
So, do you see my screen?
Here, we'll check.
Get the show.
Nothing at the moment.
So,
Try again.
yeah.
Okay, something's coming up now. There it is.
You do. Here's it.
Try presentation mode. We can see your
I
PowerPoint.
already started.
Oh, okay. Maybe there's a bit of a lag, but currently we can see the PowerPoint, but it's not in presentation mode.
You see it now? So,
Yes.
Yes, we see it now.
Yes.
okay. Good afternoon, guys. Our colleagues here in Middle East and Europe, and good morning for everybody in the United States. Happy to be with you today. I will have a chance for reviewing the hydrogen steel making routes, just basic background about what took place in the few last years, so that we all know what is the effort which was done from the steel makers in this, let's say, last decade or last 2 decades in a couple of slides. So allow me to present you something today in that regard. First of all, just one nice slide, which I always like to present about the different routes of steel making, which we all know about it, the blast furnace route, of course, which is more common, let's say, in the States and Europe, but more common is the electric arc furnace route, which is more common here in the Middle East, either from starting from direct reduction plant to electric arc furnace, or even from scrap direct to electric arc furnace. This is more common route in our region, and then going to the different caster options. One nice slide, which is bringing us to our today's topic, the reduction agents or the various reduction tools that we nowadays steel makers are using. Most common tool, let's say, the carbon one, which is our blast furnace using the coke, going down to another more, let's say, environmental friendly one. We could go to natural gas or direct reduction option using natural gas, or down in the few coming years to the hydrogen option. Another option to go to electricity or electrolysis or electric arc furnace, which is the third, let's say, option in the triangle. So these are the 3 main options in reducing our steel or reducing our iron ore, carbon, hydrogen, and electricity. Having a quick overview about the various steel routes, again, we have in terms of CO2 emissions, We have the blast furnace oxygen converter, or we call it the BOF route, which has the maximum or the highest CO2 emissions in our portfolio. Goes up to more than 1,700 kilograms CO2 per ton steel. If we go to a bit more friendly, environmental friendly options, then it will be the direct reduction with the electric arc furnace route. And then in that case, we rely on natural gas rather than coke and coal. And then we go down to around 900 kilograms CO2 per ton steel. If we will choose, and this is now the trend, or this is now the all steel makers are trying to go through, and we will explain this more in details, to substitute the natural gas by hydrogen, then it is then pretty much clear then the CO2 will drop much further to 400 to some 400 kilograms CO2 per ton steel. And if we really go to green hydrogen, relying on green renewable energy, renewable electricity or electrolysis, then in that case we can reach theoretically down to zero CO2 emissions. Again, in terms of routes, main routes, now we have the blast furnace route, which we know it's already our reference here, 100% CO2 emissions. We go down, we can, if we go switch to direct reduction plant, so we can reduce by like 35% CO2. And if we go for renewable, or, and I took here the example of Thomas Buergler, which he will present more in details in his coming presentation. If we will take now the exchange membrane, the proton exchange membrane, DRI, electric arc furnace, which means here hydrogen over a renewable route, so we can go much less in CO2. What is green steel? Green steel is a steel that we can produce through much easier, flexible, short flow sheet, like producing steel via scrap, or via manufacturing recycled material, or through offsetting CO2 and buying CO2 credits. This is like, let's say, a bit more greener steel. But what we are looking for, or what we are all targeting, is to go for zero carbon steel, which is not, unfortunately, the case right now. We are still talking about research and development and pilot plans, but we didn't reach this level stage yet. So, but now this is in the end our target, to go for breakthrough technologies, which I will explain now shortly, to end up with zero CO2 emissions using hydrogen as the main option or main target. If we are talking about hydrogen, and now it is more clear now for us that if we substitute coke or carbon or coal by hydrogen, then the CO2 emissions will drop by far, because then the off gas will be more like steam rather than CO2. Then we need to understand what's below or what's classified under hydrogen. We have the green hydrogen, and green hydrogen here is the hydrogen which can be produced by electrolysis of water. So we decompose the water to hydrogen and oxygen, or maybe we produce green hydrogen by a proton exchange membrane, as voestalpine is trying to do now. Whatever, but by any renewable clean hydrogen way, then this we call it green hydrogen. But this will be available on long term. This is not an option right now. Another option is the blue hydrogen, which is somehow in the middle. So we produce hydrogen by steam reforming, by steam methane reforming, but we have to combine this process with carbon capturing system, carbon capturing storage system, so that we can, let's say, separate the CO2 coming out from this production facility, and this will be available on medium term. Not really mature process yet. And we have the let's say the state of the art, or the available technology right now, which is producing hydrogen out of steam reforming again, but without any carbon capturing. And this is available now, but of course with CO2 emissions. So these are the three types of hydrogen which we are having or we want to have in the future. Another definitions for hydrogen, quick one, the fossil hydrogen, which is a traditional one, which comes out of fossil fuel, comes out of coal or comes out of oil or comes out of natural gas. So we call all these types of hydrogen fossil hydrogen. Another type of hydrogen is the brown one or black one, which comes from, let's say, less traditional facility or less traditional route, the coal gasification, but this causes more CO2 emissions and more greenhouse gases. Well, this is now the core of my presentation today. So what are the breakthrough technologies we are, the researchers and steelmaking plants are working on now? We will start now with ULCOS. ULCOS is a project which started, let's say, almost 2 decades from now. And this stands for Ultra-Low CO2 Steelmaking. This is a European Union project, which I was proud that I took place or I shared in this project during my PhD study as well. And this ULCOS project had the chance to end up with a mature or promising process now called HISANA process. We have another research program, or another research topic, which is Course 50. This is Japanese technology, and we will also explain it. Recent projects, which also, apart from ULCOS, took place recently and started and in the phase of development, are the hybrid technology, which is adopted by Swedish Steel, SSAB, and another technologies which are adopted by voestalpine, which is hydrogen future, hydrogen plasma smelting, and HIFO, which will be, I assume, explained more in details by Thomas Buergler. Apart from this, let's say, partnership projects, there are also stand-alone steel projects, which are also in the same, let's say, trend, using hydrogen for having 0 or less CO2 emissions, are done by ThyssenKrupp, ArcelorMittal, and Salzgitter. All these mentioned projects now will be explained process by process in the coming slides. Well, going to HISARNA. HISARNA is really very nice, promising project. As I said before, this is coming from ULCOS project. It used to be also 2 old technologies. It is simply like we see in the photo. It will rule out the blast furnace, so no need for a blast furnace, and we will start with iron ore fines. We will inject it, or we will put it to the vessel, this blue vessel, the smelter, and we will add coal with it. So the coal will reduce the iron ore fines, but in the end, we will manage through this HISARNA process to reduce 20% from the energy, as well as CO2, 20% CO2 emissions. So this is let's say, a good step in the let's say, the target of the whole project. With this combined capturing of waste gas, CO2, if we invest further, and this is a step later, if we invest in capturing, then with the CO2 emissions will even go to 80%. What is this HISARNA coming from? This is started with the, let's say, old process. It's a merging of 2 processes, the CCF, which is a cyclone converter furnace, which is here again, the top of the vessel, we can see it's like a cyclone. We inject the iron ore fines in this cyclone, and then it goes in cyclone motion down to the molten bath. And during this motion, then the pre-reduction stage to take place up to 20. And that's why we can save up to 20% in energy and in reduction in the reduction agents. So this was already proven some way back in Tata Steel IJmuiden, and they invested in a 20-ton pilot plant back then. Also, HISMELT was also investing in a pilot plant back in the 80s in Max Hütte. And this pilot plant was in this smelter part. And then combining, and then they invested later on in a commercial plant with 80 tons per hour in Australia, in Kwinana. And then they combined both processes together to end up with this Hezana, which was adapted by ULCOS, as we said, in the early of 2000s. Very promising process. We are all optimistic that it will take further steps, and we are waiting for much more results. Second process, the Swedish one. This is, we call it the hybrid technology. As we said before, this was done by the Swedish Steel, among other partners. It is simply, they are trying now to shift from the blast furnace route, which is the pelletizing the iron ore, and then going to the blast furnace among the coke plant, and then to the BOF. This is a conventional route. No, they want now to go with non-fossil fuel rather than fossil fuels to produce the iron ore pellets. And then they want also to produce a clean or green hydrogen out of electricity, and then inject the hydrogen rather than coal, reduce the iron ore, put it in the electric arc furnace, and end up with crude steel in the end. So it is much more cleaner process, going from the blast furnace to shaft furnace based on hydrogen and based on electric arc furnace. As we can see the figures, it will go from much high 16 CO2 emissions to much less one, 25 kilograms CO2 emissions, but on the, of course, nothing for free. We have, in this case, to invest in much more electricity. So rather than negligible electricity, they have to go for above 3,000 kilowatt hour electricity, but then clean steel. The roadmap of this process now, they already started a couple of years back in feasibility study, in R&D. Now they started already in a pilot plant and in producing hydrogen, producing also hydrogen. And now they are now intending in the coming 2 years to go for a transformation for this shaft furnace, which I explained, for going for demo plant, with the end target to go really from blast furnace to electric arc furnace in the 40s. So in the end target is by 2045 to go for fossil-free process. Second process, which is the first Alpine one. This is now already started in Linz, in the first Alpine Linz. This is, as we said before, this is called PEM, or stands for Proton Exchange Membrane Electrolyzer. It's 6 megawatt power electrolyzer with 1200 cubic meter per hour hydrogen production. Very nice, promising start as well. And this is, again, as we see in the process. So you inject water, you electrolyze the water, decomposes to hydrogen and oxygen, and in the end, this is pure clean hydrogen or pure green hydrogen, coming out of electrodes. But then in the end, you have, let's say, when we upscale this process, then you have also a good, reliable way to produce hydrogen and use it either in the blast furnace or on the shaft furnace or the direct reduction furnace. Then this should be the next step. So this is the hydrogen future one. Some photos from reality. In 2018, they already they built the electrolyzer in Linz, as we said. They implemented modules, and now it is already in the operation already since March 2020. Very nice, appreciated effort. Well, this is now the second also research program from First Alpine, which I'm also, or I was also proud to be a part of it in the research phase in University of Leuven back then during my PhD study. So I used to make experimental work for this hydrogen plasma process, but this at that time it was only 100-gram lab scale process, and now First Alpine is proud that they upscaled this in Donawitz, in the other side of First Alpine, up to 50 kilogram with a power input of 250 kilowatt plasma. So basically, this is you feed iron ore or iron ore fines Very simple like that, no need for pelletizing. You feed the iron ore fines through hollow electrode with additions, and then you inject plasma, very high energy intensive one. So you reduce the iron ore through the plasma or through the electrical energy imposed. And then in the end, you end up with just steam, pure steam in the off gas and pure iron. So a very simple direct process. So where you transform iron ore to pure iron in one simple project without any CO2 emissions. So a very, very promising process as well. And I'm quite sure that we will hear good results out of it. The third, let's say, project out also voestalpine Donavitz. This will be the HIFO or the hydrogen-based fine ore reduction. This is also based on pellets concentrate, no need for sintering, no need for pelletizing. And then the idea of it is to reduce iron ore fines also by hydrogen. So by natural gas and then by hydrogen. So again, this is compared to the, let's say, the much more mature process like Finmet, which is already has commercial reference plants, or Midrix, which is much more common in our region. Then this will be a good, nice also option going direct from iron ore fines to pure iron. HIFO, they also started now building, let's say, a pilot plant in Donavitz. So very promising, also with a roadmap to end up with 20% less CO2 emissions by 2050. I'm not quite sure or quite updated what is going on with the progress of this project now. But again, Thomas might update us with this project. Okay, so this is now the standalone, let's say, project or steel makers what every steel maker is doing now. ThyssenKrupp, one of the most or the biggest steel plants in Europe and in Germany, they decided to go to have their own way, and they started already for injecting hydrogen in the tuyeres of the blast furnaces to reduce the coke and reduce CO2 emissions as well. They also in parallel decided to invest in a direct reduction plant for on a trial scale, and after that they will upscale it to a commercial one with also a target to be to publish some commercial state-of-the-art DRI electric arc furnace route sometimes in the 40s or let's say 50s. So as we can see, this is the milestone that everybody is aiming at now. By 2045, 2050, everybody believes that he will be capable to have mature state-of-art processes based on hydrogen and shaft furnaces, clean small one, rather than the blast furnaces combined with the electric arc furnace with almost no CO2 emissions. Another project or another steel plant, this is Salzgitter, also in Germany. Yeah? I have 2 slides more.
Okay.
Karim. Who's talking?
I'm just giving the 1-minute warning. Thank you.
Yeah, okay, I have just 2 slides. So Salzgitter, this is also another project. They decided they chose HYL process. So HYL process is also a technology which is also known here in the region. And they decided to invest in this project and to inject hydrogen. They started with natural gas, and then they replaced the natural gas by hydrogen, also with the target to go for hydrogen electric arc furnace route rather than blast furnace. So this is also a project by Salcus or by Salzgitter, with the end goal also by 2050 to go down to only 10% CO2 emissions with reference to the blast furnace now. Last one here is ArcelorMittal Hamburg, which also decided to go for a shaft furnace, but not HYL, but Midrix one. And it will be a pilot plant, 100,000 ton a year pilot plant, and also with hydrogen injection rather than natural gas to end up with pure steam. and they also believe that in 5 years they will have the commercial mature process to publish some new figures. And last slide again, sorry for that. This is the Japanese one, the Course 50. These guys, they are more focusing still on the blast furnace and the hydrogen injection of blast furnace. They are now in this phase, in phase 3, which is again hydrogen injection in the blast furnace, and with the end goal again to have hydrogen steel making mature process by 2050. Thank you. Thank you, Karim.
Thank you, Dr. Badr, for your presentation. Of course, we'd like to thank everybody for joining the webinar. For those that may have joined a little bit later, we're taking questions on the Q&A tab on the bottom. Please post your questions there. We will get them to all our panelists. We also will try to get to most of your questions during this webinar, time permitting. However, and I should turn on my video, my apologies. If we do not get to your questions, our presenters will try to get to your questions afterwards and reach out as best as possible. Also, this session is being recorded and will be available to everyone on the AIST channel on YouTube in a few days. So also you can reference that later on. In terms of a question, there is a question that came in and says, thank you for the presentation. With the current blast furnace technology, we are able to produce iron from raw material that has low percentage of iron oxides. Do you think that with new DRI process, we can produce iron from low, I'm assuming, quality iron ore?
Well, a good question. Well, that so easy is not the case, unfortunately, because of course we know now that HYL and Midrex processes, they have more iron ore quality demands. This is the case, but in the end we can still live with it. You can live with less quality iron ore. This is not a problem. It is in the end will be only at the expense of the productivity. But this is the case now if we are all targeting a cleaner environment. So again, maybe we will start with some less production figures, but in the end, with some optimization, we will be capable again to go to the benchmark. So this shouldn't be a bottleneck for the future aim of having a cleaner environment.
All right, thank you, Dr. Badr. I think we will move on to our next presenter. I would like to introduce, maybe if we could transition to the next presentation in the process. I'd like to introduce Dr. Thomas Buergler. Dr. Thomas is born in 1967. He graduated in mechanical engineering at the Technical College in Linz and metallurgy at the University of for Mining, Metallurgy, and Materials in Leuven. He's the head of R&D, Ironmaking at voestalpine Steel Division and CEO of the Competence Center for Metallurgical and Environmental Process Development, K1-MET in Linz and Leuven. Lecturer for Process Technology at the University of Leuven and Material Science at the Technical College in Linz. Please welcome me for our next presenter here, Dr. Thomas Buergler.
Yeah, just a moment. I will open my presentation. Okay, I hope now it's in the full screen mode. Yes, no?
Yes.
Yes, perfect. Yeah. Thank you for the introduction. One correction, I have only a master's degree and no PhD. Yeah, I will give you an overview about the CO2 reduction hydrogen projects of voestalpine. And I want to start with this picture. Just a moment, I will close this window. I want to start with this picture, why we are doing all these things. And this is for me, a very impressive picture. That's that's a view about 250 years of global temperature increase. The so-called warming stripes shows us the difference between the average temperature from 1971 to the year 2000. And if the stripe is blue, then it's below this average temperature. And when the stripe is red, then it's over this temperature. And you see, within the last 20 years, we run in a more or less serious problem because the temperature is increasing permanently and all the red is concentrated within the last 20-25. The red color is concentrated in the last 20 to 25 years. And we are happy to have this here in Austria because in Vienna we have the longest available temperature record in the world. So we have continuous measurements, systematic measurements beginning in the year 1775 here in Austria. And this is besides Stockholm, this is the second largest, or one, two, these are Stockholm and Vienna are the two longest temperature records in the world, where every day is done a measurement at the same location. Next picture, yes, and this picture leads us to the Paris Agreement. We want to keep the global warming below 2 or better below 1.5 centigrade before compared with the pre-industrial period. But we are still on this. There we have to reduce our CO2 emissions, and when we do nothing, we will follow more or less the red line with the actions which the countries committed in the Paris Agreement. Then we follow the dotted line, but we have to follow the blue line to come down with the emissions more or less until 2050 to zero, because the European Union Green Deal says that we have no net emissions of greenhouse gases in 2050, and in Austria we are much more rigorous. In Austria we will have 100% renewable electric energy in 2030 and climate neutrality in 2040, 10 years before the European target. Let's look to voestalpine projects, and what you see here is the voestalpine site in Linz. It's a 6 million ton crude steel production here in Linz, a fully integrated plant with coke oven plant from the left. Then you see the sintering blast furnace area, the steel making, and the rolling and finishing lines in the south of the plant. And we have a second site in Donawitz in the mountains, in the Alps, and there we produce up to 1.8 million tons of crude steel. And in total, we produce in Austria between 7.5 to 7.8 million tons of crude steel. And we are the largest CO2 emitter in Austria. voestalpine, with the two sites in Linz and Donawitz, is responsible for 15% of Austria's CO2 emissions. So this is a very large number compared with other countries in the world. Karim mentioned also this picture. This is the way also voestalpine is proposing. We are now on the classical integrated blast furnace BOF route, where we have 100% CO2 emissions, and we only see the way that we make this technology shift from the blast furnace BOF route to the DR shaft electric arc furnace route, first with natural gas, and then in the second step with hydrogen from the PEM electrolyzer. And the CO2 emissions with the hydrogen route are only depending on the CO2 concentration, CO2 load of the electric energy. But you see also with this intermediate step with natural gas, there's a big reduction of CO2 emissions, and the amount of CO2 reduction is only depending on the ratio of scrap in the blast furnace and again the CO2 concentration of the electric energy. I have to say, the moment the CO2 concentration of the electric energy in Austria is 200 grams per kilowatt hour. Yeah, this is the voestalpine transformation way. We start now in the year 2020. We see an intermediate step is in the next 15 years to follow let's so-called a hybrid concept where we operate both technologies parallel. And then at the end of these 30 years, between 2020 and 2050, we want to switch over to 100% to hydrogen if the hydrogen is available. Because I have to say clear, the hydrogen for large amounts of iron and steel making is not available in the moment. And when you compare the price with natural gas, then the same energy unit is 4 to 5 times higher in price when you compare natural gas with hydrogen, because it's depending on the electric energy price. Yeah, what are the key projects of voestalpine? We already have decided to install an DR shaft, but not here in Austria. We installed this plant. We started with this plant in 2016 in Corpus Christi in Texas, United States. Because for us it's a very good place. There is in the future renewable energy available. Now we have natural gas supply. We have a good connection to with an overseas port. And so we have the direct connection from Texas to Austria, but also we investigating the electrolyzer technology. We want to learn more about upscaling of the electrolyzer technology, and are these electrolyzer modules ready for large-scale CO2 production? This is clear. This is a very small plant with 6 megawatts. When we want to replace the carbon in Linz 100% by hydrogen, then we don't need a 6 megawatt plant, we need a 3000 megawatt plant. So this is a very, very, very large electrolyzer plant. And from how much area, which is how big should be the area for this electrolyzer plant, then you can imagine then 100 megawatt is around 60 by 40 meters, so 2,400 square meter is a 100 megawatt electrolyzer plant. So it's not so big what you can expect from this plant, but this is only a demonstration plant. It's one of the largest PEM electrolyzer units in the world. Yeah, first we started with the HBI from Texas in our blast furnace operation. We are able to charge up to 200 kilogram HBI per ton of hot metal, and with this you can reduce the CO2 emissions of the blast furnace approximately 30 kilograms per coke equivalent by charging 100 kilogram of HBI. This is not a new experience. This is well known for several decades from other companies, but it's the use of HBI in the blast furnace process is the first step to reduce the CO2 emissions of the classically integrated process. Then we have to think about what now we operate the DR shaft in Texas with natural gas, but the plant is ready to replace 1/3 of the natural gas by hydrogen. This was designed during our pre-project in the year 2012-2013, that we can replace 20,000 cubic meter of natural gas by hydrogen when the hydrogen is available in this 2 million tons DR plant. And what is now on the market as the MEDREX natural gas hydrogen process. We are also involved in a project in the United States, the GISH project, Grid Interactive Steelmaking with Hydrogen, where we want to demonstrate the full scale of hydrogen production, of steel production with hydrogen from the production of renewable electric energy, electrolyzer technology, storage, direct reduction, and also electric arc furnace operation, where we work together with American universities in the United States, steel producers and gas suppliers. And this project started on the beginning of this year. Okay, then we have this project H2 Future in Austria, where we want to test this new electrolyzer technology with the PEM. We expect an efficiency of the system maximum of 82%. And this is really what we want to demonstrate, full scale hydrogen production. And this plant can also be used for grid balancing, grid stabilizing of the electric network when there is too much or too less electric energy in the system. So the electrolyzer can also run in two modes, full production at full capacity and also fluctuating production. Karim mentioned also these pictures, you know it already. We started with this project in the year 2018, and we are now the plant came into operation end of the year 2019. Yeah, we can operate this plant between 1.5 megawatt and 9 megawatt. This plant can also used for dynamic response. What I mentioned, we reached the stack efficiency, and we have very high purities of hydrogen for the steelmaking. This is no hydrogen quality as for fuel cells. this is not a 3.0 for fuels, there's a need a 5.0, but for the metallurgy, for a reduction process, 99.9% hydrogen is enough. The oxygen we don't use in the moment, but there are a lot of other applications for the oxygen also from this plant. Yeah, we do several tests with this plant, and we now in a so-called quasi-commercial operation till end of this year, and then the project is finished, and we are looking now for ongoing projects, for follow-up projects to test more, to do more tests with this plant, and also to use hydrogen in the plant. In the moment, we introduce the hydrogen in the coke oven gas network, because this plant has one big difference to other plants. We produce a pressureless hydrogen with 150 millibars. Yeah, what are the breakthrough technologies? What we are thinking, also Karim mentioned it. This is the hydrogen plasma smelting reduction process. We started from a fundamental research project at the university in Leoben and did now the upscaling to the plant, to our test plant at the Donawitz site. This is only a picture, but the plant is in operation. We have finished the commissioning and starting now with the trial program with this plant. And here we can produce directly crude steel from iron oxides with hydrogen in a DC electric arc furnace with a power consumption of approximately 250 kilowatt. But we have a second project in Donawitz, the so-called HIFOR project. That's a reduction of iron ore concentrates in the fluidized state. It's a project led by the lead in this project has Primetals, and we work also here together with the University of Leoben, voestalpine, and the Metallurgical Competence Center. Here we test a new technology, also in batch operation mode, not in a continuous mode, for direct reduction of sponge iron in fluidized state. Yeah, but these are all research projects. What is for us, what I mentioned already, the next step until the end of this decade, until 2030, we want to implement a hybrid technology, hybrid steelmaking. We want to install at the Linz site and the Donawitz site one electric arc furnace, which we supply with the HBI from Texas, a part hot metal and scrap. And with this concept, we can reduce the CO2 emissions at the site by 60% for a dedicated amount of crude steel. In the Linz case, is this in the first step 1.7 million tons of crude steel, and in the Donawitz case 0.7 million tons of crude steel, where we can produce a steel which is reduced, where the CO2 emissions are reduced by 60%. And when this technology is ready and hydrogen is available, then we can switch over with the beginning of 2035 to the next step. Let's say this is our hybrid project from Sweden in Austria. We can also think about installation of DR shafts here in Europe, here in Austria, and combined with the electric arc furnace, and we think about an upscaling of the HIFOR and the SUSTIL process and supply this with 100% hydrogen. But it is clear in the moment the hydrogen is not economically and in large scale available. On no location in the world, this is clear. There's a lot of discussion about hydrogen, but to have hydrogen projects, I don't see a big amount of hydrogen within the next 10 years. And so we want to do in the moment research activities for hydrogen, for plasma smelting reduction, for direct reduction, and we can think about the upscaling in the year 2035 to be ready in the year between 2040 and 2050. Yeah, and this leads me to the end of my presentation. I like the left picture very much. The COVID crisis in the moment is more or less over, and the two scientists are happy, but the scientists have to look back and what is coming behind them, and then is the big challenge, that's the climate change. And another picture is from a study from Roland Buergler, steelmaking now with the classically integrated route, the hybrid mode with the integration of an DR shaft in the plant, with small amounts of hydrogen, with the implementation of an electric arc furnace, and the final step to make green steel production with full scale of hydrogen, DR shaft, and electric arc furnace at the site. This is more or less the concept every steel producer here in Europe is following now. And yeah, we will see how we will talk in 2050 about the year 2021. Thank you for listening, and I'm happy to answer your questions.
Thank you, Thomas. And my apologies for the mistake that I made earlier.
No problem.
For correcting that, I appreciate it. So we did. I do have a slight announcement to make. We are taking Q&As in the Q&A tab below. Please, put them there if you can instead of the chat. And there is a question that came in. Hello, what do you do with O2? Question mark. So I'm not. It's a little bit broader, but he's not sure what he's referring to. Maybe the O2 supply, but you can.
Yeah, it's clear that in the moment with this small electrolyzer plant, we produce 600 cubic meter of oxygen in the hour, and here at the Linz plant we need 70,000 cubic meter. So in the moment we find no economical way to use this 600 cubic meter. But when a plant is fully supplied by hydrogen, then you produce so large amounts of hydrogen that only 15% of the hydrogen, of the oxygen is used in the plant. And 85% of the produced hydrogen is then open for the market. So these electrolyzers will change the business model also of gas producers. Because then there's a new source for hydrogen. You don't need more or less the air separation plant, or not for, but then you think, okay, well, how to produce the natural gas and how to produce the argon, for example, the nitrogen and the argon. So the electrolyzer technology will also change, I think, the business models of the gas producer. But at the moment, we don't use the oxygen for the small demonstration plant.
Excellent, thank you. I see Amr Abdelghani. Dr. Amr, you have a question? You have your hand raised? Oh, okay. Maybe that's just by mistake. So, okay, but if you want. Okay, so the next announcement we'd like to make is that the AIST MENA chapter is a provisional chapter that was formed by AIST for the MENA region. The aim of the chapter is to provide technical content in the steelmaking for the MENA region to serve the topics and the purposes of the region technically. We of course welcome participation. We also have multiple sessions that we hold throughout the year in the form of webinars, and once a year at the end of the year, calendar year, we hold a forum, a technical forum over a 2.5-day period that was held virtually due to the coronavirus situation. So we'd like to welcome everybody to join the programming for the AIST MENA chapter. Dr. Thomas Buergler, Mr. Thomas Buergler, thank you very much for your presentation. We will now move on to our next presenter, as I do not see any other questions that have come in, so we will move on to our next presentation. For the next presentation, we have 3 presenters. It's being led by Mr. Alberto Briganti for the combined efficiency of green HBI DRI with smelting technology in the MENA region. To introduce the next 3 presenters, we'll start with Mr. Alberto Briganti. He's born in Milan, Italy in 1963. Started his career as a civil engineer in SMS Group in 1992, gathering experience in designing turnkey plants for flattened pipe mills. After several years in design and engineering department, the Milan-born engineer was transferred to sales department, becoming shortly afterwards a sales director, and later appointed to the managing board and CEO of the SMS Italian subsidiary company. Throughout his training and his entire career, he always remained loyal to his hometown, except when in 2017 he began a new experience in the flat rolling plants business unit as the executive vice president for our headquarters in Germany. Currently, he holds the position of chief sales officer for the Italy and MENA region. Joining him in the presentation is Mr. Andrea Linari, as General Manager of Sales for the Electric Steelmaking division. And Andrea Linari graduated in 2003 at Padua University, Electronic Engineering with focus on digital communication. He started his career in a small company active in geolocalization of public fleet transportation sector. In 2007, he joined SMS Group as the automation engineer for electric steelmaking and continuous casting. After a few years, he became part of the technical support team for sales activities worldwide, focused on the product line electric steelmaking. From 2015 to 2018, he was in charge of the sales activity for the Far East region. In November 2018, he was appointed General Manager of Sales for electric steelmaking with global responsibility. Besides sales activities management, he is now involved in SMS Group's electric arc furnace development plan from 2020 to 2025. Additionally, we'd like to introduce Guido Bonelli. Mr. Guido Bonelli is the head of Ironmaking sales at Polworth, Italia, one of the largest branches of the Luxembourg office for Polworth SA, South America. It's owned by SMS Group. Mr. Guido Bonelli earns a bachelor's degree in chemical engineering at the Università degli Studi di Genova, with a specialization in environmental protection technologies and a thesis work performed in Germany. Guido started his career back in 2000 in former SMS DMAG as an engineer in the environmental protection department, and in the course of 10 years took several different assignments in the technical department, culminating in the overall technical management of big EPC projects in India. Since 2011, Guido has been moved to the sales department, and in 2017 became responsible for the overall sales of Polworth, Italia, in the iron division. Please join me in welcoming all three presenters. I would like to remind you to turn on your videos where possible for your presentation, and to Andrea, if you could share the presentation, it would be appreciated.
The video, I don't know, says that is the presenter that shall leave the authorization to start.
Correct. So Andrea is able to share his screen now. You should be able to see it. I see it on my screen in the presentation mode. Yes, thank you, Andrea. Looks good. Without further ado.
Is it on the screen now? Should be on the screen in presentation mode, okay?
It's on the screen, yes.
Okay, so Alberto, please.
So, as we said, the combined efficiency of green HBI and DRI with smelting technology in the MENA region is the argument. I will introduce the argument mainly related to the economics basic, and my colleagues will go more in deep regarding the process for DRI plant and for electric arc furnaces.
Alberto, can you turn on your video, please? You and Guido also turn on your video if you could.
I tried, but it's written that we cannot do, because it's the moderator that should let us.
Maybe Brian, you can adjust that and give them the ability.
Same for me.
Same with Guido. Okay, it looks like Brian will work on that in the background.
Okay. Now is okay.
Yes. Yes.
Good. So some facts of the position of MENA region about steel production. On the right side bottom, there is a table showing that already in 2019, in the MENA region, there was almost the 50% of production made by respect to the rest of the world, made by DRI. And we are talking about more than 50 million tons. That is based on natural gas flow sheet because the gas in the area is abundant and cheap. And downstream, the DRI plant is feeding mainly EAFs because to produce high quality steel with the advantage that the power prices are also very cheap. Naturally, now there is the first question whether this equation MENA equal great natural gas availability at low prices will be also in the future valid. And go to the next. And the second point, as already mentioned from the previous presenter, is the topic of the environmental footprint that has been dramatically imposed in the future from the Paris Agreement. So we can discuss about the values, but it's clear, and here we are talking about the direct emission of CO2, that there is a dramatic advantage gap between the two integrated routes that are blast furnace with basic oxygen furnace converter against DRI with electric arc furnaces. It's clear that the scrap based, that is also interesting in this area because there are a lot of scrap based electric arc furnace. From the point of view of the emission, is the most friendly solution. But the DRI is starting with a big advantage respect to the blast furnace route, but this advantage will be not sufficient when will be imposed the carbon border adjustment mechanism for the import of the steel. In few words, that means that in the future, starting from EU, the most of the consumer, for example, the automotive producer, will be forced to buy even to a higher price steel made as green as possible. Even this price will go sky high. Next. So then this is a glimpse into the future of the steel production that what are the trends as we have already seen also from voestalpine. One is that in EU that are mainly based on blast furnace route, they will have to the producer decarbonize the production and need huge quantities of green HBI to feed the new electric arc furnaces or the existing blast furnaces. And in the long term, new DRI installation and then based on hydrogen or partially or fully will replace the actual installation. But that is not valid only for you, but will be valid for all the region like China, India, and CIS, where the integrated route of blast furnace is predominant. MENA is starting in a good position that is right now in a situation where the most of the production is coming from DRI. And therefore, as an advantage to transform the steel into green steel and DRI in green DRI. Also because, as you can see in the news that we extracted from one local newspaper, in the MENA region there is the most advanced renewable energy projects, thanks also to the climate condition based on solar farms and windmills. Then shortly, just an overview what is the concept from the group SMS Polvort towards a new green steel making. On the left side, we can see that EU, as I said, China, India, and Russia are mainly based on blast furnace and BOF, and we consider this configuration, the configuration producing 100% CO2 emission. These countries will have to make several investments, for example, enhancing the blast furnace, substituting BOF with electric arc furnace, and then making installation of carbon capture, utilization and storage system in order to reduce this emission with a lot of investment. But if we look where is standing the MENA, is standing on the middle top part of this screen, where you see the DRI plant based on natural gas and EAF that is already starting against the blast furnace in several steps of revamping after revamping to reduce the CO2 content. Therefore, there is the easy solution or easier solution to go towards a H2 solution that is producing the green DRI with the best technology in the world that is worldwide recognized as Midrex, fed by a large stream of hydrogen produced through electrolysis with renewable energy. It's true that that is not immediate on short term, but in my opinion will be faster than what I heard before. Now I leave the stage to Guido for more detailed presentation of the system.
Thank you, Alberto. So we wanted, after this introduction, to present some of the solutions that our group could provide, especially looking at the MENA region market, where, as you correctly said before, there is a very high concentration of DRI plants. What is important to know is that from the present configuration, the present flow sheet envisaging the use of natural gas, it is right now possible to increase up to 30% of hydrogen, the feed to the plant, without any significant change into the plant setup. The Midrex technology is ready to receive higher rates of hydrogen. Already in the natural gas process, the gas, the reducing gas going to the shaft furnace, has very high concentrations of H2, and Midrex has already experienced in some plants where a steam reformer were used instead of the catalytic reformer, concentration of H2 up to 80%. So this is to say that into the present configuration of the plants, it's possible to have an easy retrofit in order to provide hydrogen, and again up to 30% hydrogen. No modification to the plant configuration is needed, just some let's say operating process parameters adjustment. Next, please. As we discussed before, and we heard from the previous presentation, the present issue, therefore, in developing a much greener steel production is the availability of natural gas, of hydrogen. And talking to hydrogen, we know there are many different technologies. We already heard about the PM technology, and we want to focus now on two existing technology. The first one is the traditional alkaline technology. We call it the established because it's the predominant one right now. is a proven technology which is working since many years and is ready for large scale up. But the efficiency is not very good. In our vision, and in the previous slide, it was mentioned Sunfire, the company Sunfire. The future of electrolysis is represented by the SOEC. So the solid oxide electrolyzer cells that we used to call the game changer, that has a much higher conversion efficiency, because basically they start not from water but from steam. This is very interesting because into the European integrated plants, steam is available practically at no price. But also in plants where we just have the DRI plants and DF and the downstream, the steam can be produced inside the plant itself. Of course, there is the possibility for every customer to rely on hydrogen, let's say, over the fence. But as we heard, even if there are many projects on the paper right now, it's probably not envisaged that this hydrogen will be available in a very short time at very good prices. So the opportunity to produce his own hydrogen dedicated for the operation of the DRI plant, in our vision, is something that could be very interesting for our customers. Next, please. So now we want just to show you where we see there is the possibility of producing this steam for feeding the SOEC cells. And by the way, it was mentioned, for example, the project of Salzgitter, the ULCOS project on Salzgitter. In that case, the electrolytic cells has been provided by Sunfire. If you move on in the presentation, we can see two places where we can recover the heat to produce the steam to be sent to the SOEC. And it is basically in the two places where you see, so before the top gas scrubber and after the heat recovery of the midrex before the flue gas stack. And with this scheme, we already calculated that it is possible to produce all the hydrogen needed for having this 30% replacement of the natural gas. All this with a power input of around 140 megawatt. We call it stepwise conversion. Another spot where is for sure possible to recover the heat to produce hydrogen is on the EF. This might be also very interesting for customers that don't have the Ironmaking section, but that has just the EAF. So we envisage to recover the heat at the before again the flue gas stack after the primary off gas suction line, to send the steam generated in this way into the Sunfire SOEC and to produce the hydrogen which is needed to feed the burners of the EAF, with in this case with a very modest power input of about 12 megawatt. The last slide that shows putting all together these possible heat recoveries, just to mention the fact that with this configuration we will be able to produce the hydrogen which is necessary to have also either a 50-60 natural gas replacement or a full hydrogen flow sheet, of course, of a plant of smaller dimensions, about 0.5 to 0.6 million ton per year of DRI. And the power input in this case would be in the range of 200 to 250 megawatt for 1 million ton per year plant. Very quick slide showing our references in the MENA region together with our strategic partner Midrex. The one on the left is Tosiali, Algeria, which is these two plants are the two biggest plants in the world. The production, nominal production is 2.5 million ton per year of DRI. And in particular, the one on the left has already set the world record production of 2.3 million ton per year of DRI for a single unit in 2020, despite the difficult situation due to the pandemic. The plant on the left has been put in operation just at the beginning of this year, and we are completing all the necessary testing phase. So if we shift to the next slide, I will pass the word to Andrea.
Okay, thanks Guido. Thanks Alberto for the introduction. So now we have we're gonna have a few slides more about a little bit an insight on the electric arc furnace. In the sense now we have been talking about a lot, of course, the reason about blast furnaces and DRI module, but at the end of the day and the end of the game, we also recognize the electric arc furnace will play a very, very important role in the decarbonization process. So of course, the vision in the future, we hope in a midterm future, is to have an integrated plant with DRI module, let's say driven by hydrogen, with the Sunfire electrolyzer cells, multiple of it, according to the needs, of course, and a hot charge connection to an electric arc furnace. This technology, hot transfer conveyor, of course, is already available, delivering hot DRI at temperature 550, 600 degrees to the electric arc furnace. The furnace must be a furnace, I call it fit to the purpose of DRI. There are, of course, today there are already a lot of furnaces smelting DRI using electricity, of course. But now we are talking about the potential improvement of the performance, having in mind the decarbonization aim, the decarbonization purpose. So we have, of course, we have addressed three main, let's say, fields that need to be improved. First of all, the best utilization of the available power. Of course, we are aware that in many locations, there might be not so strong a grid, electricity grid available in the Middle East or also in other regions. And this, of course, could create troublesome when you are introducing a very high demanding power electrical furnace. Second point is to reduce as much as possible electricity consumption, electric consumption. That means at the end of the day, reducing direct and indirect carbon footprint. Third point is a little bit more detailed one. Everybody's aware that when we are handling, of course, DRI inside the furnace, there's a lot of generation of slag. So a lot of energy is going to be lost in the slag, not only energy, but also some rich material like lime addition, carbon, which has no time to react in the furnace, but will be lost. So one key point is to handle the slag in the proper way. So we spent some 4 more minutes for each of these main items, just to give you a little bit on our inside view on the future of the electric arc furnace for DRI. First point I would like to touch is the utilization of DC technology on electric arc furnace for DRI. This is very important in the specific when we are talking about big heat size furnace, 240, 250, 260 ton furnace that could cope with 2.5 or even bigger modules of DRI. Here we have a need of energy which is very high. So as active power we are required to have 180 megawatt, okay, which is a very high power. And this code we are very at the limit also of the electric current capability of electrodes. That's why we have a design with a DC furnace using 2 cathodes and 1 anode, okay, where the current is split between the 2 cathodes. And the nice things about having 2 DC parallel, let's say, circuit is that the arcs are attracting the one to each other, as you can see in the picture. So we are creating a very well-defined, clear area where we have available the maximum power. This is not possible with AC furnace, conventional, in the sense that the high density zone in AC furnace is in the middle of the electrodes, which is a very narrow space, very difficult to reach, but it's possible with this configuration. So we can increase the feeding rate of the DRI, we can increase the density, the power density for melting the DRI material, keeping or increasing the productivity. And even in the future, with the introduction also of a relevant portion of cold DRI, these configurations still have, I would say, some safety margin to add even more power, because we have no limitation on the electrodes like we have today on the AC furnace. Second point, which is strictly connected to this DC technology in electrical furnace, is the utilization of what we call ORA, which is an IGBT chopper technology. So we are talking in replacing the very well-known heavy-duty transformer for feeding the power to the electrical furnace, and replacing with a number of modular panels, like the one you can see on the right. So we are transforming the furnace from, let's say, a dirty load for an electrode to a clean load. It's like a motor. Instead of having direct starting, you have inverter starting of the motor. That means that the disturbance to the network are very, very much limited. There is no need to install a static var compensation, because the load is now a clean load. Okay, and furthermore, you get rid of all these I call it auxiliary electrical power devices like transformer, reactors, filters, switch breaker, all of items that need, of course, relevant also cost in maintaining and operating. This is a modular solution, so you will install a number of modules according to the current and power that you need. This, of course, change also the approach to the spare stock of a plant. You can have only one module in spare stock and then 6 or 7 modules running. So this is also a view into the future, because as we said before, electrical power, electricity availability will play a role. So we need also to work on this respect. Third point, which is, as I mentioned before, a little bit more, let's say, process relevant, is utilization of what we call a slag valve. So far, in a conventional furnace melting DRI, you start the slagging after 10-15 minutes. And you keep the slagging for 20 minutes. Okay? So there is quite a lot of waste of energy. You cannot keep the slag inside the furnace, giving the right time for all the elements like carbon or lime to react in proper time. So with this solution, with the automatic slag door, we can actually seal the furnace and keep all the slag inside the furnace for the time that we need. And this will bring, of course, saving electricity, of course, a saving electrodes, but by far more important, will increase the yield of the DRI melting. Okay, so we'll increase the yield of DRI to liquid steel. And also we are going to lose by far less material in terms of carbon, in terms of lime, because they're going to have more time to react inside the electric arc furnace. This is already in operation in many plants that are working with scrap, but also with DRI. As SMS, of course, we have been active already in a DRI furnace, DRI plant. We are just to mention 2 references already existing running, one in Bahrain, in Sulb. We are talking about 130-ton electrical furnace, this is running with 100% constant, of course, hot DRI. Hot DRI, the temperature 560, 570 degrees Celsius at the input, let's say, of the electrical furnace. This is in operation since almost, I would say, now it's 7 years. Yes, 7 years. Second reference, which is going to be, is already installed, as now is starting a commercial production, is in Oman for a 1.2 million. In this case, this is working with HBI. And you see also in the picture, this furnace is already working with this automatic, I call it condor, is what I called before, kind of slag valve for handling the slag inside the furnace. So of course we are ready to challenge also the future challenges of H2 DRI in a modern electric arc furnace. Now we'll leave just for a conclusion, and we'll leave the word to Alberto for the last slide.
So the last slide is recalling the first slide where we took away the blast furnace and basic oxygen furnace, and we started as a reference the actual DRI with EAF fed by natural gas, and what the solution that we presented, we believe that we can help our customer to go towards a dramatic reduction of the CO2 direct emission, both in the route integrated from DRI and the route from scrap-based EAF. Thinking in this way, more economically, that could be the future, also to have access to several customers in the world. Thank you very much.
Thank you for your presentation. There was a question that was posed earlier, but it was in regard to sharing the presentations. I did answer it by text, saying that these presentations will be available because the entire session is recorded and will be posted on the AIST YouTube channel, which would be shared with all the registrants of this webinar in the near future. I have no other questions that are posted at this time. However, I'm looking at
There are a few questions in the
there are
chat.
the questions on the chat, right? Okay. So for everything with okay, here it is. So I think that the first one is posted. Thanks, Karim, for your presentation. Current blast furnace technology, we are able to produce iron from raw material, low percentage of iron oxide. Oh, this was, I think, Ashraf's question that we already answered. So I'll move on to the next. Thanks, Guido, for the presentation. You mentioned using EAF fume to produce hydrogen. Can you please give us some information about this? Also, you mentioned injection H2 in EAF. That will have negative effect on final steel quality produced.
Yeah, okay, I'll answer to that question.
Sure.
Of course, I mean, of course, we are going to test the solution. We have already tested the solution in a laboratory scale, and we're moving a little bit to implementation. As a matter of fact, the mixing, we also will have a step-by-step conversion, no? So moving not directly from, let's say, 100% natural gas to 100% hydrogen, but we go for a mix of natural gas and hydrogen. Yes, you're right. There are two main points that we need, of course, to be careful. We know, everybody knows that the hydrogen is a different flame temperature, has a different temperature speed. So there are a lot of things that need to be studied. We are not worried about that. We are pretty much confident. We have already a good characterization of the flame. The impact of hydrogen on the steel, of course, in terms of quality, no, for pickup of hydrogen is something that we are going to study. We are going to analyze with some real cases. It is, of course, on the top list on our, let's say, analysis that we are carrying on right now.
Thank you, Andrea. The next question is, Dear Guido, thanks for the presentation. What about the SOEC? Any pilot scale projects for hydrogen production via the off-gas heat recovery? And how big is the hydrogen production?
Sorry, I'm not sure. Yeah, to have correctly understood the question. So the cells are available. I mentioned the module that was supplied by Sunfire for the ULCOS project. Right now, the installed power of available for Sunfire is something around from 750 to 1 kilowatt to 1 megawatt. And of course, this is modular. So this is provided normally into standard containers with all the equipment on board, and the cell, let's say, a module like this normally can produce around 200 normal cubic meter of hydrogen per hour. I don't know if there was another part of the question that I missed, or
there was a question about any pilot scale projects for hydrogen production.
Mm-hmm. Yeah, the one that I mentioned, for example, is one of it. Sunfire right now is very active especially, let's say, in the Scandinavian market for this kind of scales projects. Of course, their production right now, we cannot say it's really an industrial production, but they are growing very fast, and we see very, very good opportunities to scale up to a real industrial production in very short term, especially if all, let's say, this need of hydrogen will continue to be the base for the steel industry conversion to green steel.
Okay, now there's a few more questions that popped up in the Q&A. I will go through them as quickly as we can here. First one is are there any EAFs in construction or operation with double cathode and one anode design?
Yes, there are. They are not so popular. I tell you true in the past, because of course also of some capital cost investment, but now this electronic cost is going down, so now it's a totally competitive solution. Yes, there are. There is one in Far East in Japan and one in the Americas. So they're already existing. Is nothing, let's say, completely R&D project, but it's something already well proven. Yeah.
Yeah. Thank you. The next question is actually, we have to be careful here because it mentions cost, but are there any EAFs in construction or operation with Aura technology? And what is the capital cost savings versus conventional setup? Instead of saying cost, maybe you can answer by percentage savings or something like that, instead of mentioning any direct cost savings.
Okay.
The antitrust guidelines, please.
Okay, about the first question, I mean, the same technology has been in use in the United States for, I would say, 15 years in a SMS furnace from 2000 until 2012 or 2013. No? There was a kind of pioneer project for this using chopper technology, which is the correct name. Okay. After the period, of course, we were waiting. Of course, this project, this furnace gave a good result, but we were waiting for it to be competitive also on installation cost. That's why now we have waited a little bit, a couple of years, and now we are ready to let's say promote and of course ready to install this plant. As a matter of fact, with the new configuration of the Aura, there is no plant so far, but we have started promoting these again relatively few months ago. So it's a brand new product, but it's already well tested. Second point was a little bit, now I missed that one, was the cost saving or...
Yeah, the capital cost savings versus conventional setup.
Well,
and maybe
without talking about figures, just I think everybody of you is a little bit aware of it. With this system, you get rid of transformer, you get rid of static var compensation. Okay, so you get rid means that you don't need to install it. Okay, and also a very important thing is that the power factors that I forgot to mention of this device, of this equipment, is very high. Power factor is 0.95. So you buy 1 megawatt and you use 0.95. Today you buy 1 megawatt and use 0.78. Okay, so immediately you will see that also the bill from this point of view, in terms of authority on the authority grid on the network, will decreasing. Of course, you have some additional cost installation, but you cut the cost of SVC installation and a reactor and transformer. So it's pretty much a well-balanced proposition. At the end of the day, the OPEX are much more.
Okay. Next question, and unfortunately we can only take one more, and then we have to move on to the next question. What are I don't know which one to pick here, but let's go with
the first
environmental. There's an environmental question. What are the potential increase in other emissions like NOx and N2O while reducing CO2 in the use of H2?
No, well, it's of course is a good question. I mean, in parallel, I mean, there is not. I mean, I present only some highlight technology. In parallel, we are also working very hard on a total sealed electric arc furnace. Okay, of course, we have the issue of the flame. The temperature of the flame of hydrogen is even higher than the one of natural gas. So we need to take care about this increase of temperature, which could also cause some increase of NOx. That's why in parallel, we foresee the use of this burner together with the sealing of the furnace, with the sealing door, continuous charging of DRI, so not opening the roof. So we are creating a sealed environment, okay, where the atmosphere is inside the furnace is always a reducing atmosphere, not an oxidizing. So in this way, we would avoid the creation of NOx.
Okay. Well, the other questions, we'll see if we have time to address them at the end. I would like to introduce our next presenter and speaker, Dr. Amr Abdelghani. Bring up the bio. Okay, Dr. Abdelghani is an assistant professor at the Chemical Engineering Department, Faculty of Engineering, Cairo University, Egypt, since November 2018. He got his PhD in metallurgical engineering from the University of Utah, USA, with a research focused on a novel flash iron technology to produce iron from magnetite. Dr. Amr founded his own company, Al-Rafai for Engineering Services, which is a certified partner for Flow 3D CAST program in the Arab countries. Please join me in welcoming Dr. Abdelghani for his next presentation, the steps to produce greener iron in the MENA region.
Thank you, Karim, for the introduction. Let me try to share my screen. Okay, it's working properly. You
Yes.
can see my screen now.
Yes.
Okay. Hi. Thank you so much for the introduction, and thank you all for staying to the end. So my presentation today is about steps to produce greener iron in the MENA region. First, I would like to give you like a quick outline of what I'm going to talk about today. Quickly, again and again and again. I would say all the people were talking about the DRI process. I'm not gonna talk that much about the process and production of iron from scrap. I will little bit talk about more about emissions and pollution coming especially for the MENA region. And then I would say it's all about the source of the energy. To say we are going greener, we have to look to the source of the energy. Then finally, I'm going to talk about challenges and recommendations for greener iron production. First, DRI process. Like I wouldn't spend almost any time on this. All the presenters before me talk in details about how DRI process is major at the MENA region and how it's like 50% production of the DRI process of the whole worldwide is centered in the MENA region. I would like to look quickly into DRI process and say that as the presenters before me mentioned, it's all about natural gas. Why we are focused here on DRI process? Because it needs natural gas. And natural gas is cheap in the MENA region. Natural gas is mainly methane, which is CH4. So focus with me on this. CH4, this is like a very important thing for the DRI process. When you start from the raw material, whatever raw material you have, most probably will be hematite. But natural gas is a very important thing that favors the DRI process in the MENA region. Another thing which is like related, another DRI process, which is HYL. We have the methods and HYL. And also like talking about production of iron from scrap, which is something that lots of manufacturers at the Middle East will use when they like get a scrap and use electric arc furnace for the production of iron, and then afterwards go for the continuous casting and the final production. Here you can look into that and think about, okay, that needs electricity. You need electricity for the electric arc furnace to melt the scrap, produce the melt iron, and afterwards like going for the continuous casting. Even the process of rolling, all of this needs lots of electricity, and electricity is a very important thing here. I talked very quickly about this. Let's talk a little bit about environmental. emissions and pollution. Look to the worldwide and see cause number 5 for one of the major causes of health issues. Number 5 over there, after high blood pressure, smoking, high cholesterol, you will find the ambient particulate matter. And particulate matter are like materials, or you can say in simple word, dust. Sometimes we cannot see it, but if it is like, if there were like some sort of pollution, or there were some sort of like sand or anything, emissions related, or like something from the burning of coal, you will have like particulate matter there. And this is actually number 5 at the highest emissions and pollutions. And when we look to the worldwide and look to the map of the whole world, and here we can see like the particulate matter concentration, something called particulate matter 2.5. And particulate matter 2.5 means that the size of your particles, which are suspended on the air, is less than 2.5 micrometer. And when you look into that map, you can like clearly see there's a big issue with the MENA region. Like this is something that is big thing, and even this is like 2.5, less than 2.5 micrometer. Even when you like try to look into particulate matter of less than 10 micrometer, PM10, you will find like the highest things ever would be Riyadh in Saudi Arabia. This may be not only the pollution, but also the sand and dust, but there is an issue because some other areas like the MENA region is highly concentrated with particulate matter. This is a problem, and this is a pollution problem. Another thing that we were talking about before, we were talking about electricity and producing of electric arc furnace, like using electricity to produce iron. And we call this as, this is very nice, a very keen and very nice thing. But when you think about the source of electricity, you produce electricity from electrical power plant. Electrical power plants are using natural gas, and one of the recent electrical power plants are being produced, are being like manufactured in the Middle East, are produced from coal, even coal, and very new like power plant stations from funds from big countries would give funds to developing nations, and that electrical power plant will use coal. But when you like produce electricity, it's not that clean, because coal, as you can see here in the picture, it would have some traces of mercury over there. And mercury, when it burn it, it's gonna go to the air and then have deposition. And when the mercury fall down, precipitates on water and rivers, mercury would go there and would react in something called methylation. And when it reacts in methylation, mercury will be accessible to all the aquatic life in rivers. All the aquatic life, like fishes, which we eat afterwards, will have traces of mercury, which is a heavy metal. And also even birds, when they eat fishes, they will have some sort of mercury. So the thing is that about electricity, although we like to make everything coming from electricity, but electricity sometimes is not that clean energy, because it is associated with CO2 emission in a sort of words, as we can see from this. Looking into the MENA region, you can see like the countries here for the MENA region, and I just wanted to show the map again, because I know we have lots of attendees who are not from that region, and that region has lots of countries over there. For the MENA chapter, the AIST MENA chapter, regional chapter, we have like 25 countries so far on our chapter, and this is like a big with different like with different like I would say prosperity and money. People from Gulf country may have some luxury, but this is not the same with all of the countries in North Africa. With other countries, it's there are fluctuations and differences over there. What I'm going to talk about is I talked about electricity, I talked about natural gas, and I talked about this big issue of particulate matter that we have in that region. Now, my question, which I will answer to the rest of like maybe 10 minutes left over there, what about the source of energy? Can we like use source of energy that is green, that can help us like moving and saying that we are producing iron, greener iron? The presenters before me, they covered it very nicely about hydrogen and hydrogen for the manufacture of iron. But I will talk about a little prospect that is different from the environmental point of view. And talking about the source of energy, I have here 4 renewable sources of energy. First one, which is waste to energy. Second one is geothermal energy. Third one is very popular, which is like the solar energy. And fourth one is very popular as well, which is the wind energy. Talking about each of those as a source of energy that we can use it, we can integrate it into production of iron, that will make our iron greener. I'm not going to say it's going to be green, which means like 0 emissions, because we know this is not like a very accurate word. We would have some sort of emissions over there or something on the production of the material over there. But we are aiming to have like greener iron. First source of energy is waste to energy. So waste, we have lots of wastes over there. Like source of waste are biomass from agriculture waste, or like sludge from wastewater treatment plants. The first one on the left top picture, this is sludge coming from the wastewater treatment plants, and then agriculture waste, biomass agriculture waste on the top right, and then on the bottom left, we have the agro-industrial waste, which are like things, traces from the, whenever you use for industrial production of juice, like orange juice over here, you would have agriculture industrial waste coming from that process. And the last one, which is like a big issue in lots of countries of the MENA region, which is the organic fraction of municipal solid waste. We call it like huge trash coming from the people. We have large population over there. We are like more than 300 million, and we have lots of organic fraction coming from our daily waste over there. And those are not well used in recent days or nowadays. And how to produce waste from energy? The answer is one of the technologies that is very, very promising and I'm going to say promising, I'm going to say it's well-developed technology, is the anaerobic digestion. And anaerobic digestion will use lots of those wastes that we talked about, like sludge from wastewater treatment plant and slurry from wastewater treatment plant and even like other biomass organic fraction of municipal solid waste, and will supply them into digester. And this digester, it will like produce biogas. And when it produces biogas, the biogas will go from the top, as we can see here. That biogas is mainly contains 2 things, CO2 and methane. And when you separate the CO2 from the methane, at that time you produce methane. It's not called like regular methane or natural gas. We call it biomethane. And that biomethane or that methane is a green source of energy. It's not based on like the regular methane from the ground. It's based on like garbage and waste that was doing a problem. And you use it to produce methane, and afterwards you can use the methane integrated into your DRI process. And when you try to add it even by small percentages at the beginning, this is how you can like convert to be like little more greener in your iron production. And the waste that is coming afterwards, which is a solid waste, is going to be a natural fertilizer. This is called digestate. And digestate is a very good thing for earth, and we can use it for like organic plants and all of these applications. Another source of energy, and I will try to be a little faster over here, is geothermal energy. I know this is not like that big or more commonly used at the region, although it is a very promising energy. Where it used like where you inject like water into the surface layers of earth and making use of the heat below the earth to generate steam from that water. This will be hot water, and it will be steam afterwards. And that steam, when it goes into generators, will produce electricity. And that electricity coming from the production from geothermal energy is a renewable source of energy. It is a very promising energy that is like being studied a lot in developed countries like America, United States specifically. And you can see here, this is a map that was like generated, which shows like distribution of geothermal resources in USA. And I hope that we would have such a map for the MENA region, where we can like spot places of geothermal energy at the MENA region. However, because of like efforts, like a very like most recent publication on of like geothermal energy in the Egypt, specifically in Egypt, where it produces like where this map shows the concentrations of geothermal spots in Egypt. It was published by a researcher. He's a colleague of mine and close friend, Dr. Mohammed Al-Karmouti. And this is actually thanks to a funding they got it recently from European Union, where they like with help of other universities in Europe and Cairo University, mainly in Egypt, the BI of the project, were like generating a map and testing and making like that map of geothermal hotspots in Egypt. I'm hoping this effort will go afterwards and be more and be spread over the MENA region. Another source of energy, which is solar energy. You can see here a map shows like the hotspots of solar energy at the MENA region, and our MENA region is a very, very good potential place for production of solar power. And electricity coming from solar power is a renewable energy, and we can use it in the electric arc furnace, and this would make it like more greener iron for the production. Same applies for the wind power dynasty, which is like we have here a map shows like the wind power potential areas where you can like use from the wind and the speed of the wind, you can put like the equipment where you can like generate the turbos that can generate electricity from the wind, and several spots over here in Algeria, I would say Tunisia and Morocco, they are very promising, and Libya as well, and Egypt, even like for the Red Sea, places like Sharm el-Sheikh and Hurghada, they are being used effectively now and they are using it to generate renewable energy. I wouldn't much about like the waste management because this maybe take more than the time that I have left. So I would skip that slide and I would talk quickly about the challenges that we have right now to apply this idea of like renewable energy in iron. Number one is the certificate of origin for renewable energy. It's very important, like where you produce electricity from renewable energy source, it's a renewable energy, right? But when you connect that electricity to the public grid of your country, it's no longer like renewable energy. You need to have like the same source and connect it directly to your plant or to your like factory of iron to say this is like renewable energy being used over there for electricity. So having a certificate of origin for renewable energy, this is a very big challenge at the countries, at the MENA region countries. Of course, investments, as I said, like a quick example of the geothermal energy, something that needs investment to check over there. Also for the waste to energy, although it's a well-developed technology, but it's not like commonly used in MENA region. For example, I can tell you that a country like Italy, they produce renewable energy from waste that is equal to combined renewable energy from all other sources, like wind, plus solar, plus dynamic or hydro energy. All of these together, all of those energies are equal to the waste to energy that they produce in Italy. And also on return on investment, this can be used easily by like looking into using like well-developed technology, and lots of suggestions are on a technical readiness level is something that is 8 and 9. So it will have return on investment. My recommendation, we need to think about being a greener. To be green is difficult and looks like very difficult and long path. But thinking about greener and adding more and more is a very good thing to apply it as a mentality at the MENA region. We need to have more involvement from chemical and environmental engineers. I'm a little biased over here because, as Karim mentioned, I'm an assistant professor in chemical engineering department, and I also work in environmental engineering. But having involvement from multidisciplinary, not only metallurgical engineers like myself, I'm a metallurgical engineer, is very important and very good to make it greener. And some paperwork is needed on a state level to have that certificate of origin, to have like people who authorize and give certificates of origin of renewable energy. This is paperwork that is needed on a state level. Thank you so much for your patience, and I'm sorry for like taking that much time, and I'm done with it. Thank you.
Thank you, Dr. Ablegani, for your presentation. Especially like the maps about where geothermal, wind power, and solar energy concentrations are at for effective use of green energy. So I appreciate that. Considering the time, we have a question that's posed from our chair of the AIST MENA chapter, Mr. Mohammed Saeed, engineer Mohammed Saeed from EZDK. He'd like to pose a question to all the presenters today. In your opinion, to which extent do you think MENA region is prepared to adopt the clean steel technology as a summary? And we'll start with Dr. Badr and address it through the group to end the series for this webinar.
Okay, thank you, Karim. Thank you also, Muhammad, for the question. Well, let's differentiate between two things, between our topic, today's topic, which is environmental issues, and the clean steel in terms of new steel grades, new qualities, which could even increase our product portfolio and make us more competitive in the international market, having these clean steel grades. So yeah, back to the question, clean steel here means another investment in new steel plant facilities, in closed casting facilities, in flat product, in bloom casting, etc., which is unfortunately not the priority for the current steelmakers here in the region. The steelmakers in the region are more interested in producing rebars and billets, because this is a construction steel, which is still the countries are in need for, with a high profit margin. Going for clean steel, you have to invest in really too much capex, in vacuum cleaners, in vacuum degassers, etc. And in the end, you are not pretty much sure if you will market in the local market or not. So people are more thinking in investment and in money and in profit margin. They are not thinking about clean steel. So we are not mature enough yet to have this in the region. Thank you.
All right, Mr. Thomas Buergler. You're muted.
Have you? It's not working?
It's working now, yes.
Yeah, okay, that's working now. Yeah.
So the question is, in your opinion, to which extent do you think MENA region is prepared to adopt the clean steel technology?
They already have the clean steel production. They only have to transform from natural gas to hydrogen. So, and they have the best production conditions for the hydrogen production. It's only to invest in hydrogen electrolyzer technology. From my point of view, based the PEM technology.
Thank you for a quick summary and answer. Appreciate it. The same question poses now to SMS Alberto Berganti and Andrea and Guido. In your opinion, to which extent do you think MENA region is prepared to adopt the clean steel technology?
I can try to answer. Let me say that from the starting point of view is probably the best region in the world, because they have the possibility to produce renewable electrical energy, having a lot of spaces. They have already a lot of DRI plants. There will be in the near future a lot of demand of green DRI, HBI out of the European steel producer. The question that I think we cannot answer is the political intention really to invest in such a direction. And that is difficult to answer.
Understood. Thank you, Alberto. And finally, Dr. Pagani.
Yeah, I would second Dr. Alberto and what he mentioned, that we are very promising region for adopting the clean steel technology. However, I would like to add, as he mentioned, we need some sort of initiations that to be applied, and we need some laws. We need the power of the states, the power of each country to be applied over there, and asking those plants to have certain range of limits and certain range of pollution limits. We talked a lot about carbon and carbon tax and all of that carbon tax that people are talking all the time about. It can be applied, it will help to make it cleaner production. But we should think that this can be applied in just no time, and we should spend more investment, more research to be prepared to that point where we would have to pay to the country for because of our CO2 emission. I think we are very well prepared, and I hope that preparation will be supported by investment and having R&D a part of the plants to be prepared to the day where they would need to produce like way lower CO2 emission from the iron.
All right, thank you. Well, we have a couple of slides here to thank our sponsor and our presenters today. This webinar was sponsored by Heister. We thank them for their support. Heister is today's webinar sponsor and a global manufacturer of forklifts, high-capacity lift trucks, and container handling equipment for the metals and steel industry. With strength, durability, and a range of electric power options, Heister can help you meet sustainability goals without sacrificing performance. Please visit heister.com to learn more. Brian, do we have another slide? Or yes. So the 2021, we'd like to let everybody know that 2021 MENA Steel Forum, which is a 2.5-day event, is being held from Tuesday, the 30th of November to Thursday, 2nd of December, 2021. It's a virtual event, and please visit AIST.org. It'll be covering much more topics related to the MENA region and that could be of interest to the global community. However, it is specific to the MENA region. So thank you all for your attendance today and your participation, and we look forward to seeing you in future events. Goodbye, everyone.
Thank you.
Thank you.
Bye.
Thank you.